You would be hard-pressed to find an area of science or technology that hasn't been dramatically impacted by recent advances in nanoengineering. Fields that are seemingly unrelated, like medicine, electronics, and even cosmetics, have benefited by the introduction of nanoparticles. We all know that the most distinguishing features of nanoparticles are their size. The word nano corresponds to a length scale that is 1 billion times shorter than a meter. But beyond just size, in nearly all applications, a nanoparticle shape is known to have a significant impact on particle properties and behavior. Therefore, the ability to predict or even tailor particle shape is crucial for improving performance. But how do we actually go about this? A great demonstration of this idea is thermionic cathodes, which is the focus of my doctoral research. Thermionic cathodes are materials that emit a ton of electrons when they're heated up. When we use high power electron microscopes to view them up close, like this picture on the left, we see that the tungsten grains all have the same shape. But here's the problem. The list of steps used to make cathodes is so complex and convoluted that it's honestly impossible to figure out exactly which steps are actually contributing to forming the shape. So I took a step back and approached the problem from first principles. I worked to identify the specific combination of temperature and chemical environment that could produce this characteristic shape. But there's a major obstacle. Results from first principle quantum mechanical calculations are always at 0 Kelvin, which is absolute zero. This isn't really a great approximation when cathodes are being operated at over 1,000 degrees Kelvin. My work is focused on incorporating finite temperature into these calculations so that we can get a bigger, clearer picture. I use supercomputers to study how these systems vibrate at the atomic level and extrapolate the energy of different surface configurations at a range of relevant temperatures. Since the shape of a nanoparticle is directly related to the ratio of surface energies, I can actually create a predictive map of nanoparticle shape as a function of temperature and oxygen availability. Check out the image on the bottom right. Not only can I tell you the shape, I can even tell you what surface complexes think the arrangement of atoms are most likely to be present. So instead of dealing with an insane manufacturing process, we can get right to the point. I can tell you precisely what temperature and oxygen availability will yield the exact shape we want, and we can fabricate it directly. And the best part is that this is a general approach, meaning we can apply it far beyond cathodes. In any case, when nanoparticle shape is important, if you have a particular surface that's best at filtrating contaminants, that's holding onto drugs, or directing light, let's build it directly without wasting any space. The greatest part of science is that no one person can do it alone. All of our work is connected, even if it's not obvious at first glance. Thank you all for your attention, and I hope you're all staying safe and healthy.